Okay, so you're gonna hear a lot of times math people claim, oh, this statement holds for every natural number, and there's infinitely many natural numbers. So how do they get to claim this thing, right? How do they really know that something's gonna be true infinitely many times, basically, right? So this is where we get to proof by induction. Now, I guess I should specify it's proof by mathematical induction. I remember taking a philosophy class one time where, they talk about how you're not supposed to uh, say that something's true using inductive reasoning. You're supposed to say something's true by deductive reasoning or something like that. But yeah, proof by induction is like one of the biggest techniques that mathematicians have. It's almost like I saved the best for last because, yeah, no matter what part of mathematics you're doing, it doesn't have to be number theory. It could be analysis, could be geometry, statistics, probability. Uh, Basically, proof by induction comes anywhere. Abstract algebra, I believe so. Where you least expect it, there's probably gonna be a proof by induction needed to be done somewhere, always. Okay, so once we go over what a proof by induction is, we'll be finally ready to feel confident that we can prove any statement that comes our way. This will be the last. Well, maybe not the last, but definitely it's a good closer to finish this series about proofs. So let's get to it. Okay, so one of the most recurring techniques we're probably gonna see, right? So mathematical induction. I'm just gonna keep saying induction, but I mean it's mathematical induction. All right. In true me fashion, I wanna give you guys something though. By the way, so this is from actually last video. We're not gonna get to this right away, right? I just want to since this whole series is about techniques of proving things, right? So one of the tautologies I gave you last time was this, that basically proof by cases, right? If P or Q implies R, well, if and only if each of them imply R. P implies R, and Q implies R. So we have basically we have the or on this side, right? Well, what would have happened if we would have had the or on the conclusion instead of the hypothesis, right? So then, what if we had P implies Q or R, right? How do we deal with that statement? Well, this one is equivalent to the statements if and only if P and not Q, this thing implies R. So again, if you want to check that this is a tautology, yeah, you would do a whole truth table for this, truth table for that, and hopefully they match everywhere, right? So yes, so this is if P implies Q or R, then proving this statement is the same thing as proving that P, assuming P and assuming the negation of Q, has to imply R. Well, so again, I'm not gonna do a truth table, but instead I'm gonna give you an example of how a proof like this goes. Because this is also a statement that I probably should have given you back in the Axiom of real numbers video. But it's a good thing that I held off to it because now it's a good time to show you how we use tautologies, right? So I don't know why I put up the P there, right? I should have put it here. So prove the following statement: if A times B equals 0, then either A equals 0 or B equals 0, right? So this is not an axiom, this is just a statement that we can prove. if a times b equals 0, then a equals 0, b equals 0, right? So if I'm going to use this thing, right? So that's what I mean. P, so a times b equals 0 is my p. Then let's say this is my q, and then this is my r, right? If p, then q or r. Well, according to this tautology, all I have to do is that in order to prove this statement, it's equivalent if I just prove this statement. So I'm just going to prove that if, maybe I should write it over here on the side. Prove if a times b equals 0, and if I know, so the negation of a equals 0 is that a is not 0, right? So if a times b equals 0 and a is not equal to 0, then b has to be equal to 0. So that's what I'm really going to prove. All right. Now, well, this statement I think is pretty easy. So the proof goes like this. Let me write over here. So suppose a times b equals 0, and a is not equal to 0, right? How am I gonna prove that b equals 0? Well, again, this is why I said I should have made this video back in the axioms of real numbers. Since a is not 0, then it has to have a multiplicative inverse. So there exists some a inverse, right, in the real numbers, so that a times a inverse equals 1, right? And then so if a times b equals 0, multiply by a inverse on the left both sides, then a inverse times a times b should equal a inverse times 0. Well, what am I getting at? A times a inverse is going to be 1, right? So 1 times b equals a inverse times 0. Well, what do we know about these things? 1 times anything is itself, right? So on the left side, we just have b. And then what do we know about the right side? Any number times 0 is 0. So this times 0 is 0. Right? So if 1 times b equals a inverse times 0, then we're really just saying b equals 0. And that's it, right? We did it. So that was the proof. I just want to mention real quick, if we didn't have this tautology, it also wouldn't be like the end of the world either. There's a sneaky way that I would have proven it too. Well, I don't know if it's sneaky necessarily or not, but I could also, so the original statement, right? Let me write it again. If a times b equals 0, then a equals 0 or b equals 0, right? So how would I have proven this in a different way? I would have done 2 cases, right? Case 1. My case 1 would have been really lazy. Case 1, a equals 0. And what is it to prove? Well, if a equals 0, we are done. Woohoo, that was an easy proof. I'm saying that I'm going to consider 2 cases. Well, if my case 1 is a equals 0, there's only one thing that my case 2 is going to be. Well, not necessarily. I'm going to say that this is my case 2, a not equal to 0, right? So, right? These are the only 2 cases that exist. I mean, they're not the only 2 cases that exist, but, remember when I say my tautology, P or negation of P, right? That's always a tautology. Well, that's also, in a way, if you think about it, that's a way where you can always use to split the universe, you know? Um, you know, you can always split something in the entire universe in two ways. Uh, the universe in which P is true, and the universe in which not P is true, right? So what I'm saying is that, yeah, these I think I'm taking in account every single case, right? If I say case one, A happens to be zero, and then case two when A happens to not be zero, right? And what am I saying, that if A is zero, then I'm done in this case? Well, because the statement says if A times B equals zero, then either A equals zero or B equals zero. So if A equals zero, then this statement is true, right? Again, this is my if P then Q. So if A equals zero, then the statement A equals zero or B equals zero is true, right? That's what I'm saying. It's like a cheating way, right? Where like my case one is like basically no case at all. I'm just doing it and saying I'm done. But then my case two is suppose A is not equal to zero. Well, my conclusion is that it's either A equals zero or B equals zero. So as soon as I say case two, A is not equal to zero, I need to prove that B equals zero. How would I go about proving that if A is not equal to zero, then B is equal to zero? Well, exactly what I did over here, right? So I would actually end up redoing this proof anyways. But so the advantage of this tautology is that over here, where I'm claiming, oh, I'm doing two proofs, even though this case one was no proof at all, really. I mean, it is and it isn't, you know, whatever. What this statement is telling is that you don't have to do two cases, you just have to do one case. You assume P and not Q, and then hopefully you can prove that this implication has R as a conclusion, right? So yeah, again, how would I do proof for case two? Well, basically just copy and paste what I did over here. So I'm just gonna leave it at that, right? Okay, so then now let's actually move on to mathematical induction. So before we do mathematical induction, I gotta show you this axiom. So axiom. Okay, what's this axiom going to be about? Well, this is not an axiom of the real numbers, actually. This is not an axiom of the real numbers, but it's an axiom of the natural numbers. See, here's the thing. Here's the difference that the natural numbers have that the real numbers don't have, right? The natural numbers have a smallest number, 1, right? But also, if you pick any random subset of a natural number, right? Well, it's bound to have a smallest element. It's hard to explain, but it just makes sense, and that's why this is just an axiom. This is not a theorem; it's an axiom. So we call it the well-ordering principle. The well-ordering principle of the natural numbers. So what does the statement say? It says that if A is a subset of the natural numbers, so basically this doesn't have to be the entire natural numbers, but it has to contain of only natural numbers, right? If A is a subset of natural numbers, and of course assuming that it's not empty, because if it is empty, then how are we going to say that it has the smallest element if it has no elements at all? So we're going to have to say that it's not empty so that it does have a smallest element. If A is a subset of n and it's not empty, then there exists some m for, minimum, or I suppose there exists some m in A such that this m is less than or equal to A for every A in A. Again, that's what I'm saying. Any subset of the natural numbers always contains a smallest element. That's just what this means. And again, it makes sense, right? Any subset of the natural numbers is going to always have a smallest element. But how would you actually go about proving that? I mean, well, I guess someone thought about it a lot and they just gave up and made that an axiom, which I'm fine with that because, again, yeah, I wouldn't really be able to know how to explain it other than give you a well duh, you know. And that's again, we just say they're axioms instead. Okay, but then now we can prove this thing. So this thing is a theorem. So principle of mathematical induction. So what does induction say? So suppose, all right, suppose you have a statement. Suppose Pn is a statement. For every n in the natural numbers. So meaning, you know, this looks like a function because, yeah, it's meant to look like a function. It's saying that P1 is a statement, P2 is a very similar but different statement, right? P3 is a statement, P4 is a statement, P5 is a statement. And again, I'm saying statement in the way that I defined it from the beginning, right? It's a sentence that's either true or false. So suppose you have a statement that's true or false for every natural number. That's basically what this says, right? Then Pn is true for every n in the natural numbers if something happens. Two conditions. First condition, that P1 is true. And then the second condition, anytime, so I'm just going to put if in parentheses. Anytime pk is true, then pk plus 1 is true. Where k, again in parentheses, for k being a natural number. So this is what the theorem says, right? If you have a statement, you know, that's, you know, could be true or false, for you know, for a natural number. Well, we can prove that some type of you know, some type of pattern, some type of statement. That's what Pn is going to be most likely. Some type of, yeah, statement, pattern, something that has to do with natural numbers, right? Well, you can claim that this pattern continues to be true every single time, meaning this statement is true for every natural number, assuming that it's true for 1, and then also that if it's true for k, then it's true for k plus 1. Well, what does that mean? So so by the way, A and B are my two conditions, but they're actually my hypotheses. So this is my, if this is a if P then Q statement, A and B together are my P, and then my Q statement is Pn is true for every natural number. But yeah, so if you just read it in English, what it's saying? Well, if P1 is true, okay, so P1 is true, big deal, right? But then this is the important part, right? If PK is true, then it has to be that PK plus 1 is true. Well, if P1 is true, then P1 plus 1 is true. Meaning, if P1 is true, then P2 is true. But then, if P2 is true, then P3 is true. But then, if P3 is true, then P4 is true. And you see, it forms a chain that basically keeps on going forever. Okay. So that's what a proof by induction is, that you prove it for like some base case, usually 1. And once you prove it for the base case, you also prove that every time k is true, k plus 1 is also true. Alright. Well, this is a theorem, right? So I should prove it. Proof. So actually, you'll get to witness finally, right? A proof by induction. I mean, a proof by contradiction. So proof by contradiction. right? So like I said before, A and B together are my hypotheses, and Pn is true for every n in the natural numbers is my conclusion. So remember, what was the proof by contradiction? We're gonna prove that the negation of if P then Q is always false. And what was the negation of if P then Q? The negation of if P then Q is P and not Q. So how do we start our proof by contradiction? We start by saying, suppose that condition A, and condition B are true, but so the negation of the statement, Pn is true for every n in the natural numbers, right? So Pn is not true for every n in the natural numbers. So we're gonna assume that A and B are true, but we're gonna say that Pn is not true for every natural number. So I guess this is an important thing that I should mention. The negation. See, if I say that this is not true for every natural number, and we're being mathematicians right now, right? So what when do we say that something's not true? Well, if there's at least one counterexample, then it's not true, right? So then the way to negate this statement, the way to translate the statement Pn is not true for every n is this, right? I don't know. You can tell me in the comments if I'm wrong, but this is what I'm gonna say. So there exists at least some n in the natural numbers, so that P of this natural number is false, right? Here's what I want to say for the future. The negation of for all is basically there exists, and the negation of there exists is for all. Why is that? Because if I tell you, just like I said, right, if Pn is not true for every n, well, the negation is just simply that it's not true for at least one of them, right? And then what would the negation for there exist be for all, right? Because if I say something like, say that I tell you a statement of like, for every number x that's not 0, there exists an x inverse, so that x times x inverse equals 1, right? So the negation to that statement will be that if you're gonna tell me that x does not have, if you're gonna tell me that x does not have a multiplicative inverse, then you're basically telling me that for every real number, x times any real number will never be 1. But you see how that negation of there exists now means that for every real number. I'll just let you think about that one, right? And let's go back to this proof. So again, suppose that A, B are true, and then suppose that Pn is not true for every n. So I'm just gonna translate this, Pn is not true for every n, to say this. So that means that there's at least one natural number so that Pn is false. Okay. Could be more than one, could be 2, could be 3, could be 10, could be a million, who knows, right? So because it could be more than just one, I'm going to do this. Well, consider the set S. And the set S is basically going to be the set of natural numbers, so n in n, but natural numbers such that Pn is false. Alright, so the set S is going to be basically all the natural numbers so that Pn is false. Well, what am I saying, right? So I'm saying that this n naught is definitely an element in S, right? It's not that's not important right now, but I'm gonna put it on the side. N naught belongs in S because we know that P of n naught is false. That's the explanation. Okay, but see how I constructed the set, right? I'm telling you that the elements look like natural numbers. So basically, S is a subset of the natural numbers. Actually, I can't believe that I said that. That is not important. This is important because, moreover, S is not empty. Why is S not empty? Yeah, actually, yeah, uh, because yeah, this N naught belongs in S. So what am I saying? I'm setting up the necessary conditions for me to use the well ordering principle, right? S is by definition a subset of natural numbers, and it's not empty. So thus, by the axiom I presented in this video, well ordering principle. So by well ordering, I'm just gonna leave it like that. There has to exist some M in S that is the smallest. Okay, and again I'll put in parentheses. So M is basically less than or equal to every little s that's in S. You know, that would be the more mathematical way to put it. I mean, that's what I'm saying by what does it mean that M is the smallest element in capital S? That M is less than or equal to little s for any little s in big S. Okay. Now again, right? So again, when I said that the statement was true, right? You know, I kind of showed it to you in words, right? That if P1 is true, then P2 has to be true. But then if P2 is true, then P3, then P3, then P4, right? That's the main logic of why this statement has to be false. Why this statement has to be true, right? So since I'm doing a proof by contradiction, I'm saying that everything that I've said so far eventually is going to lead to a contradiction. Can you see where the contradiction is going to lead to, right? I'm saying that M right now, this little m, is the smallest natural number in the set S, meaning is the smallest number such that the statement P is false. So what am I trying to get at, right? Let me go forward, right? So no, since P1 is true, since P1 is true, that definitely means that 1 is not in S, right? Because you're only in S if Pn is false, right? So because P1 is true, because that's the assumption, since P1 is true, 1 is not in S, right? So what I'm trying to say is that this number M has to be strictly bigger than 1, right? But if M is strictly bigger than 1, then M minus 1 is strictly bigger than 0. M is a natural number, and if you have a natural number minus 1, it should still be a natural number unless it was 1, but it's not 1, right? So what I'm saying is that M minus 1 is also a natural number. Okay? Right? M is greater than 1, so M minus 1 is greater than 0. So M minus 1 is a natural number, right? Also, M minus 1 is less than M, right? That should be not too controversial, right? So why's it important that I'm saying that M minus 1 is less than M? Well, because M is the smallest element in S, right? So M minus 1 cannot be in S, right? If M minus 1 really was in S, then M is no longer the smallest element. So that has to mean that M minus 1 is not in S. Okay, but again, what does it mean that you're not in S? Since M minus 1 is not in S, then that means P of M minus 1 is a true statement. Okay. By B, if P of M minus 1 is true, then what has to happen by B? P of m minus 1 plus 1 is true. But what's P of m minus 1 plus 1? So P of m is true. This here, right here, is where we finally reach the contradiction. You know why? Because, however, m is an S. So because m is an S, by definition, Pm is false. See, when I said how do you spot a contradiction, you know, if you thought I reached the contradiction way before I got to the sentence, I didn't. This you should know is finally a contradiction, because what am I saying? I'm saying that Pm over here is true, but I'm also saying Pm is false. So what am I saying? I'm basically saying P and not P. And again, that was one of the tautologies that we covered in the previous video, right? P and not P is always a contradiction. So when I say Pm is false and also Pm is true, that's when you reach the contradiction, right? It's as clear as water that that's a contradiction. I don't think anywhere before that is as clear as water that we reach the contradiction. But right when we get to here, it is so clear that it's a contradiction, right? So that's what we prove. We prove that the negation of if P then Q is a contradiction, meaning that it's always false. Therefore, the original statement, which is the principle of mathematical induction, is true. All right. So that's a proof. You know, if you were not impressed by this proof right here for the statement, this is the type of proof that you do all the time as a math major, right? So maybe it's scary, but trust me, you know, if you do a bunch of them, they all end up tasting the same. Really. You just gotta get used to it. So, you know, I see my video's pretty long, but I just want to add some extra stuff. I just want to add you. So that was proof by induction, right? Now, there are variations. I definitely don't have the time to prove these variations, so I'm just going to state them. So the first variation is that, alright, say Pn is a statement for every n in n, then Pn is true for every n in n if, and this one now is kind of one condition, but it's a really big, really strong condition. If P1, P2, P3, all the way until some specific pk. If P1 all the way to pk are true, then pk plus 1 is true. Now, yeah, it sounds like the exact same thing that we just proved, right? But actually, so this thing assumes, so the previous thing just says P1 is true, but also anytime pk is true, then pk plus 1 is true. This one's saying that if you happen to know that every single statement, all the way from the first one all the way to the kth one, is true, then the k plus 1, the next one, is also true. So what's the difference between this one and the other one? There will be a few occasions where the other induction is not strong enough. But there will be situations where you actually need to know that all of them, or maybe not just all of them, maybe you just need to know that pk and then the one before pk minus 1 Sometimes you just need the first two to work. Sometimes you need three. Sometimes you need four. Well, sometimes you need all of them. Yeah, again, the regular induction that I prove works for like a lot of times, most of the times even. But there will be a few cases when you're actually going to need that the statement is true from the beginning to the end to prove the very next one. And then here's the second variation. So notice how we keep starting at 1, right? Sometimes there are times where like you have this thing, this again sequence or you know, something that you notice, but it doesn't start right from the beginning. Maybe it doesn't start at 1. Maybe it starts like at 3 or at 4, right? So say Pn is a statement. So again, by just saying there's a statement alone means that it could be either true or false. So for every n in n. Suppose Pn is a statement for every n. Then Pn is true for I don't know, let's say for n greater than or equal to let's say L, whatever. If this one is back to two conditions. P of L is true, and the second condition, for K greater or equal to L, if Pk is true, then P K plus 1 is true. So yeah, this sounds like it went back to the original, but this is now saying, okay, suppose that the thing that you're noticing doesn't start necessarily at n equals 1, but it starts at n equals L. Well, you can still prove that the statement is going to be true for L and after, basically this way, you know. Again, the proof for this one is, and I'm pretty sure the proof for this one too, is very similar to the proof I just did. And again, we don't have time because this video is big enough, and I'm trying to not to do gigantic videos like I did in the prologue series, unless that's what you're into, by the way. Like I haven't seen any feedback yet, right? Well, as long at the time of this recording, I haven't seen any feedback. So I don't know if you guys prefer the shorter ones over the long ones, because the shorter ones, yeah, they're quick, but also not as much information, and maybe that's not as much fun. I don't know. But okay, so yeah, here are some variations to prove by induction, and again, it's very deductive, even though it's called by induction. So again, if you're like a philosophy person and you're not down with mathematical induction, well, it's really deductive. So I mean, I just did a whole proof. Well, all right, guys. If you stuck around this far, leave a like, comment, let me know what you think. And I think this should be the end for this series of proof. These are everything I've showed you so far is the most. This is how mathematicians usually prove stuff, either by induction or by one of the techniques that I showed. Proof by contradiction, by contrapositive, by cases, so on and so on. All right. Alright guys, see you in the next one.